Good day, everyone. My name is Lao Yong Lee. In this presentation, we will explain our log flow analysis of IEEE 14 bus system by using Power Word Simulator. The IEEE 14 bus system is a standard test system widely used to study the steady-state operation of power networks. The system operates at a base power of 100 MVA and a nominal voltage of 132 kilowatt. The network consists of one slack bus, which is bus 1, 4 PV buses, which is buses 2, 3, 6, and 8, and 9 PQ buses. The Powerwall simulator was used to model buses, generators, transmission lines, and loads. The main objectives of this project are to analyze voltage profiles and the line coding, to identify weak buses under stress conditions, and to apply voltage improvement techniques to enhance system performance.
Today, I would like to talk about the base case load flows for the title of low voltage buses, which is less than 0.95 per unit. This is the circuit before scaling, which does not increase 150% for active and reactive powers. And this is the circuit for after scalings, which is increasing 150% for the active and reactive powers. For example, we can see from the bus 14s, the active and reactive power is 50 megawatt and 5 megawatt. Then after increasing 150%, then the bus 14's active and reactive power become 22 megawatt and 7 megawatt. And this is the result before and after scaling. In the base case, several buses already operate close to the lower voltage limit, particularly from bus 9 until 14. We can see from here, the bus 9 until bus 14 is less than 0.95 per unit. These buses exhibit comparatively lower voltage levels than those located nearer to the slack and generator bus. After increasing loads to 150%, causes all buses except the slack bus to fall below the 0.95 per unit threshold, which indicates low voltage operations. We can see from here, after the active and reactive power increase 150%, then the voltage per unit will become all buses are less than 0.95 per unit. And these buses are located far from major generation sources and are supplied through long transmission paths, making them more sensitive to increased reactive power demand and voltage drops. Now, I would like to talk about heavily loaded lines, which is greater than 80% loading. This is a circuit before scaling, and this is the circuit after the scaling. This is a result before and after scaling. The line loading results indicate that some transmission lines are already heavily loaded in the base case. Before scaling, only line 1 and 2 operates above the 80% loading threshold under normal conditions. We can see from here, only line 1 and 2 are greater than 80% loading. After increasing loads to 150%, multiple lines such as line 1 and 5, line 2 and 3, line 2 and 4, line 4 and 5, and line 5 and 6 exceed 80% capacity. Line 1 and 2 become severely overloaded, reaching 300% loading, which poses a major risk to system stability. We can see from here, after scaling, we can see that a lot of the transmission lines are greater than 80% loadings, whereas the line 1 and 2 are severely overloaded, which is 300%. Power flows primarily from the slack and PV bus towards the heavily loaded PQ bus in the lower part of the diagrams.
Hello everyone, my name is Christopher, and now I'll be presenting about the voltage improvement method. So we are selecting the bus 14 as the weak bus for the voltage improvement analysis because it has the slowest voltage magnitude. So now I'll be presenting for the method. So for the method 1, we're choosing the method which is adding shunt capacitor. So because it's common and practical solution used in real power systems to improve the voltage level, and it provides reactive power support directly at the affected bus without reducing system demand or requiring major network changes. So a shunt capacitor supplies reactive power locally to the bus. When reactive power is supplied near the load, less reactive power needs to be transmitted from distant generators. This reduces the reactive current flowing through the transmission line and lowers the voltage drop across line reactance. So the voltage improvement can be explained using the simplified relationship, which is delta V is approximately to the line reactance times the reactive power. And then next, we are choosing another method which is reducing local load. This because it directly reduces system stress. Although it may not always be practical in real operation, it clearly demonstrates the relationship between load demand, line current, and voltage magnitude. When the local load at bus is reduced, both active power and reactive power demand decreases. As a result, the current flowing through the connected transmission line is reduced. Lower current leads to a smaller voltage drop across line impedance, improving the bus voltage magnitude. This effect is supported by the voltage drop and loss relationship, which is the power loss is equal to I square R, where I is the line current and R is a resistance.
Hi, I am Yong Song K, and I'm going to continue the presentation by talking about the improved case result. This is the first method we improved the result, which is using the shunt capacitor. We improved the result at bus 14. This is the result without shunt capacitor. This is the result with shunt capacitor. You can see that the PU voltage is increasing. Local compensation. A shunt capacitor was integrated specifically at bus 14 to act as a local source of reactive power. The second point is Q injection. Instead of drawing all reactive power from the main generator at bus 1, the capacitor injects reactive power directly into the tail end of the system. Current reduction. By supplying the reactive component of the load current locally, the total current flowing through the upstream transmission line is reduced. Reduced line losses. Lower line current leads to a direct reduction in the voltage drop, because voltage drop equals to Isaacs across the feeders connecting bus 1 to bus 14. Now let's talk about the method 2 to improve the result, which is reduce load power at bus 14. This is the baseline result, and this is the reduction in load power. We can see that the result is also increasing. Mitigation of overload. The baseline result shows a system that is heavily overloaded, causing extreme voltage drop across the line. Reduce line current. Reducing the lower power directly lowers the total current flowing from the source. Lower impedance drop. Because the voltage drop across a line is defined as voltage drop equals to Isaac, a smaller current leads to a significantly lower loss, allowing the voltage at bus 14 to recover. That's all from me, and I will pass the presentation to the next person for further explanation.
In conclusion, this project successfully analyzed the IEEE 14 bus power system under normal and stress conditions using PowerWatt simulator. Here are several key findings include increased system loading causes severe voltage drops and line overloading. Secondly, bus 14 was identified as the weakest bus under stress conditions. Thirdly, installing a 5 ampere shunt capacitor was the most effective voltage improvement method. And finally, improved voltage profiles, reduce system losses, and enhance overall stability. This study highlights the importance of reactive power management and voltage control in maintaining power system reliability and preventing voltage collapse. That's all from our presentation. Thank you.